All right, guys, looks like we got called out to another inspection. Let's go check it out. So we get called out of this house when an inspector does his walkthrough, and he found a few things of concern. On one side of the home, there's a pretty substantial vertical crack in the foundation wall. And then on the interior of the home, it was built with these massive timber beams all throughout the home. And one of them had a pretty severe split down right the middle of the beam. So we show up on site and we do our walkthrough around the house on the exterior first. And just at first glance, when you see these stepping cracks or diagonal cracks going through the mortar joints, that can be a really good sign that the foundation itself has moved. If we get cracks that are more vertical than diagonal and they split the brick in half, that can be a really good sign of temperature differences or shrinkage. So what are some of the questions that we look to ask when we see these vertical and diagonal cracks in the foundation wall? Number one, does it translate to the inside? Meaning if I go in the crawl space, am I going to see this vertical and diagonal crack in relatively the same location? That to me means that the whole footing itself has moved rather than just the brick on the outside has moved. Because sometimes you'll find in these older homes where the brick is built on a separate footing than the foundation wall of the home. So that's number one. We look to see if the crack is translated from the outside to the inside in relatively the same location. The second thing we look for is how fast is this crack moving? How old is this crack? There's a difference between age-related settlements and something more severe, something more sudden, like severe drought or a severe rainstorm that actually moves the soil away from the foundation, causing it to sink down or swell up. All right, guys, I kind of wanted to draw you a picture here and show you why we look for cracks on both the outside and the inside and why it makes a difference. So some of these older homes, they'll pour your house foundation. This is your footing. And then they will build your CMU foundation wall on top of that. And in some of these older homes, what they'll do is they'll build what's called a slosh footing or another separate footing for the brick. Now, this is pretty exaggerated because, of course, you want to tie these two together. But I just left a house last week that looked like this. This brick was completely destroyed, massive cracks. I mean, a 1/4 inch or more separation between these bricks. But when I went on the inside of the crawl space, this CMU looked really good. So that led me to believe that this was built on a separate foundation that was falling. So most likely that house was going to have to rebuild this brick wall. But in other news, what's happening at this house is we have this concrete footing. We got your CMU block. And then we have your brick that's built on the same footing. If there's a crack in this brick on the outside, I go inside on the crawl space and I look, and there's the exact same crack on the CMU. And that translates to me that this footing itself is moved because both the inside and the outside masonry are cracked in the same way. So that tells me that this footing itself has moved. So that kind of leads me to believe, and here's a longitudinal view. If we got CMU, you got the picture. This is your footing. You got your brick on the outside here, right? There's a crack all the way here. And that leads me to believe if I see a crack on the inside and I see a crack on the outside, that crack is translated through the footing itself. So then, in that case, we would recommend, typically, a helical pier. And it's got these screws on it. We would recommend helical pier. It's got these screws on it like that. So in theory, what we're doing here on paper is that we're saying that this helical pier is now replacing the soil as if the soil does not exist in this area. That's what we're doing. I hope that makes sense. All right, so the other thing that was going on in this house is you go on the interior and it's built beautifully. It looks like a cathedral. They have these large timber beams in the ceiling as roof trusses. I'm talking 8x8s, 6x6s, 6x10s. But one spot in particular, right near the stairs, there's a horizontal beam that catches the stringers of the stairs going up and the stringers coming down. And this one beam had a large split right down the center of the beam. So obviously the homeowner wanted to keep the beauty of these timber beams and not replace it with some typical dimensional Home Depot lumber that just wouldn't look very nice. We wanted to keep the beam in place, and we needed to figure out a way to handle the loads and keep this beam from splitting anymore. So what we decided was to put a tension strap at the bottom of the beam so that when the beam flexes and it gets loaded, all that tension force gets put into the metal strap at the bottom of the beam. I think it'll be easier to show you than to explain it. Let's draw this out real quick. You got this beam here. Okay. This is some engineering technicality for you. Statics and dynamics, if you guys know what I'm talking about. We got this beam here. Okay. We got a load that's applied somehow. Could be your joists attached to the side of it, however you want to describe it. But your beam begins to deflect. It bends down, right? And what happens is this bottom piece goes into tension, and that just means that it's pulling apart like this. It's stretching out at the bottom, and then at the top, as it begins to curl up, these pieces, top fibers, are beginning to be in compression. They're pressing against each other as you bend this beam up. So when we go to repair this beam, that's sort of what we look for. We say, okay, we got this check that goes pretty high in this beam, and we need our beam to still handle the load that is applied. So what we do in this case is we prescribed a metal strap that goes on the bottom of this timber beam. Because at the bottom of the beam is where we're going to get the most tension force, is at the very bottom of the beam. So what we're doing is we are prescribing this new Simpson strong tie metal strap to replace the bottom fibers of this wood beam. So we want my metal strap to handle all of this tension load at the bottom. So the top can still handle its compression, just like it normally would. And now we got this metal strap that is completely replacing, in theory. Of course, in reality, they're going to work together, but it's hard to quantify that on paper. So there's a lot of math involved. You can figure out what load is applied to this beam. You take the measurements of the beam, you figure out how deep this beam is, how long this beam is, and then eventually you can figure out what this tension force is in the bottom of the beam. And once you know that tension force, then we know how to prescribe this new metal strap. And I'll show you for you guys who are interested. This is the, if you can see that, this is the Simpson strong tie wood connectors. And we'll come over here. If you can see that, straps and ties. So we'll find us some metal straps in here. So it kind of looks like that. So good news for us is that Simpson Strong Tie has already done all the math. They've already done all the research, all the testing and stuff. And in this catalog, they have all of your requirements. They have all of your safety checks. They have all of your installation specifications and things like that to make sure that you can use the tabulated values that they provide for their connections. So long story short, I just want to describe to you guys kind of what we look for. We look for these foundation issues, what a helical pier kind of looks like, and why we prescribed a metal strap at the bottom of the beam. So I hope that helps. So in this case, what we found for the homeowner, what was best in our opinion, was that we would recommend some helical piers to support this vertical crack. And normally what we recommend is we put one helical pier on one side of the crack and another pier on the other side of the crack, because in theory, we're pretending that the soil doesn't exist right there anymore. So we got both ends of the concrete footing, both ends around this crack are supported now by these helical piers. And one thing that I always tell homeowners is, how far can we go to make sure the water gets away from your home? What else can we do to get water away? Do we need larger gutters? Do we need larger downspouts? Do we need pop-up drains? Do we need a French drain? Just think about what else we can do to get the water away from the house. So after our inspection and after our recommendations, the homeowner was pretty happy and he felt confident to move forward in purchasing the house, which I'm glad he did, because if he didn't, I would have bought it. I'm going to keep sharing things like this, the real things that I find on real job sites, and kind of give you what our perspective is as engineers when we go out and we do these structural inspections. If that's useful to you, stick around because I'm going to share a lot more.